Good morning, mathematicians. How we all doing today? Ready to grapple with some more extremely basic algebraic topology? Me too. Yeah. Ready to grapple with some more. Gotta realize our choice of complex is the right choice of complex. I mean, undoubtedly it is, but I want to go through and carefully verify such things. And yeah. Okay. So, what are we doing today? Okay. So, right. What am I doing here? So these are my chain maps. This is, inclusion. This is inclusion. What's the DI? What is the DI? I guess I better go back to Wikipedia. Which homology was I even looking at? Not ES. Or was I looking at singular homology? You're finally back. Well, welcome back, finally. Hello, Kostaka Corey, and just another internet guy. Welcome. What are we doing? Singular. Was this what we were looking at yesterday? No, we were doing something else. Singular homology. Simplicial. What page were we on? You finally got done with Hartshorn. Damn. You mean even the double-starred exercises? Oh, yeah. Here's where we were. Simplicial complex, I think. No. Were we here? No. No, I abandoned this one. What page was that? I guess I could open up yesterday's live stream and take a look. I guess that's what we'll do then. Short-term memories, fraud. Terrible. All of Hartshorn? Yeah, did you read it cover to cover? That's crazy. Big if true. Got done with cohomology and called it a day. Okay. Fair. Yeah. When are we going to do 4 and 5? Actually, probably the content in chapters 4 and 5 you can get from elsewhere, right? Maybe there's better sources than Hatcher. Or Hartshorn. I said Hatcher because that's what's on screen. Okay, what wiki page are we on? Simplicial homology. We're on the simplicial homology page. There are 3 open problems. Oh, and they're all in chapter 1. Oh, I didn't realize they were all tucked in there. It's true, you can get all the content from elsewhere. And possibly even ideally from elsewhere. Although I don't know, I like the section on sheaves and schemes. Nice cohomology video dropping soon. Hell yeah. Okay, so we were on the page of simplicial complex. What was the definition of the realization? I want to make sure I have my maps correct. Okay, certainly. Okay, whatever. It's got to just be the. What am I doing? It's the obvious maps. It's the obvious maps. So what do we have here? We have S0 cross delta 0 union S1 delta 1 union S2 cross delta 2. Oedipal complex. Yeah, well, does it satisfy the axioms of a cohomology theory? Has anyone checked the Oedipal complex? Okay. You can write geometric realization as a coend too. You had it in that one blog post. Okay, maybe we should check that out afterwards. Right, but what do we need to do here? So I guess we'll start at the top and move down. So what does this say? So what is E2 0, for example, is this whole region. And so D2 of E2 0, I guess, is what? It's the boundary. So I guess we call it E1 1 plus E1 0, yeah, minus, wait, E1 0. Oh yeah, the upper index, right, minus E1 2, for example. Right? So then that should be glued to what are we trying to say here? So all of the points of this form, E1 1 plus E1 0 minus E1 0, comma t, are gonna get glued to wait, what is this? E2 0. Oh, but this is, I see, right. And this is going to be all t here is in delta, that copy of delta 1. Right. So that's exactly that we're gluing these things onto here. Okay. Nice. Rest of the stream, proof that compact Lie groups are semi-simple after the stream. Nice. Yeah. Okay, I don't know. Should I do one more computation to finish convincing myself? Probably. But wait, here's where I get confused. Here's where I get confused. Because, for example, if we compute E1 0, D1, E1 0, it is homology. Yeah. If we compute this, right, shouldn't this be E0, E0, 0 minus E0, 0? Which is a little weird. Yeah. Am I just tripping again? Damn, I'm probably just tripping again. Why am I so bad at this? Clearly, I'm missing the... Where's the page? I thought I had the page that we were on yesterday, but I guess not. Because there's something with some page with the sets S. Was it the simplicial complex page? Oh. Oh, we need delta complex. I see. Hang on. Oh, delta set. It was the page for delta set. That's what we're doing. Delta set. Good morning, Tenacity. Nice. Okay, this is where we were. There we go. Right. Right. FN. No, I don't care about that. And the D is just a map from... Okay, but these are just sets, so whatever the hell I was writing about, differentials as was total nonsense. There's no formal sums. That's total nonsense. Where are there formal sums? The only possible maps here. Right. So then what do I want for my maps in this case? Hello, Jacko. What are we doing to delta sets? Computing the homology of a torus. The worst way around. Let's erase all this nonsense. There are definitely formal sums in the computation of the homology. But we're still just trying to pray for this group theory final. I will pray to Galois, maybe. No, there's people who took group theory further. We will all pray for to the math gods for you. Right. So do I just want to send what is it that I want to... How is it that I want these maps to work then? Perhaps Abel? Didn't he like die before anyone knew? Didn't he die like sick before anyone knew appreciated his proof. I think I have an essay on this somewhere back when I took a history of math course. Abstract nonsense, yeah. You just use Poincare duality? Probably. Yeah, there's a million better ways to do it than the way that we're doing it here. 17 crystallographic groups have infinite elements. Yeah, because you can translate, for instance, you should be able to translate, or translations are allowed in the crystallographic groups, right? So it should, but they're finitely generated, right? Am I crazy? Let's fact check me. Three-dimensional point group, blah, 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 lattice. Or is it just the rotation groups that we look at? Yeah, actually, what's the definition of the group? Do we just look at the rotations? If we just looked at the rotations, then I guess they're... yeah, maybe we just look at the rotations. If that's the case, then maybe they're finite. Maybe Tenacity should be able to tell us. They got a group theory final coming up. They should know. Because I was thinking we do care about the translation invariance, but we only use that to say that it's like a wallpaper pattern, right? Oh, we do want our reflections. Okay. Yeah. Yeah, okay. I have a really nice like coffee table book on this. You still can't find all subgroups of S4? Tenacity. Well, that's your homework for today. You better solve that exercise before your final. I feel like that's some prime exercise right there. I mean, here I am balking at you. I can't do basic algebraic topology. Was this day 3 of this goddamn problem? They should just kick me out. Yeah, so this has to be a set map. All subgroups of S4 is harder than the homology of the torus. Well, maybe I'm misunderestimating it. Maybe I'll go and I mean I'll try that, and maybe I'll try it after this if I ever finish this. Maybe I'll just die here at my desk not understanding basic homology. If it's infinite, how can you find its subgroup? Say P4MM. Well, which one's P4MM? P4MM was a short name. Okay, let's go see this group. Well, I mean, there's going to be a lot of subgroups, right? Like, so what? This group is generated by what, reflections across each one of these angles? I mean, just reflections and rotations, right? So just like, and if it also includes like if it also includes translations, like just look at the translation subgroup, right? Just look at the subgroup of translations, for example. Like just forget that you have reflections and rotations, and then there you go. How do you even find subgroups of Sn in an efficient way? Well, that's a harder question. Like for S4, you just see which groups can embed in S4, but this won't scale well. Yeah. Yeah. Um. Yeah. In general, it's just not easy, right? Because every finite group embeds in some Sn, so you're kind of screwed. And then also, since the order grows factorially, you're like double screwed or equally screwed. I don't know. You're just very screwed. Wow, 10-second moment of silence, Leo. I very honored that I've gained so much respect from you. Something Young diagrams. Can the Young diagrams help us with the subgroup structure? Hmm. How would we go about it? Actually, yeah, that's an interesting question. Um, I mean, start with pretty sure your uncle died of P4MM. Uh, 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 yeah, Young diagram. I mean, I would start with the cyclic groups first, because that's easy. Um, like I'm trying to think. You could then think about oh, well, maybe an option, maybe you want to look at conjugacy classes because we have a nice understanding of the combinatorics of the conjugacy classes of Sn. I wouldn't do this for S4, by the way. I think S4 you could proceed much more simply. Maybe I'm wrong. Um maybe I'm wrong. But for S4, I think you could proceed much more simply. Um, would a representation theory approach work to classifying the subgroups? I mean, if that is true, then Arad's comment about using Young diagrams maybe then would apply. But it's not clear to me how you would. It's not clear to me how you would do that. Um, it's not so clear to me how you would do that. Uh, yeah. Yeah, it's got to be pretty intricate. Have you used GAP for finding subgroups? Oh. Your thesis is about subgroups up to conjugacy. Interesting. Well, then you should be laying down how to do it. No, I don't know if I've used GAP to find subgroups, but I've definitely played with GAP via Sage in order to yeah, do some computation, some like representation theory of finite group computations. Um, yeah. Yeah, I mean for S4, like I said, yeah. For S4 though, I would just start playing with elements. I'd look at the cyclic subgroups first and then I would ask myself, okay, well, like what happens if I toss in a second, say I have an element and I have a second element that like generator that has the same thing, and then like how would I toss in what if I tossed in a second element that has um, no components in common, and just sort of do a case analysis like that. Um, I think that's probably a good approach as any for S4. Does not scale obviously, but you don't know if they can help with subgroups when it comes to, but there's always Young diagrams. Yeah, yeah, yeah. Oh yeah, yeah. Leo said the same thing. Check generators in a set of cycles and represent them in minimal form after conjugation. Yeah, yeah. But also in general, because like, is this a trick that just works? Maybe the trick just works for normal subgroups, but um, like, because I'm thinking about when you prove that A5 is simple, you use the classification of conjugacy classes. Like you use the class equation and you basically make some arguments about subgroups of certain orders existing or not. And something like that. So I don't know. You could also maybe make some progress in bigger approaches with the class equation. Do I have time? Do you have time to hear about our Lord and Savior modular forms as sections of vector bundles? Oh, I forgot. I was gonna look into that. Crap. Oh, I didn't mean to do that. Crapola. But I need to finish this. I need to finish. I really need to finish this. I really need to finish this. Oh Lord. Okay, look. God dang it. Okay, hang on 1 second. I need to decide to set up the torus. We need to know what our map is going to be from S2 to S1. Maybe. Okay, let me make a note. Let me open it up. Let's see. Mod forms has sections. We're going to leave this as a note, possibly for tomorrow, possibly for later today. Let me type the modular forms as sections of line bundles. Oh, I've clicked on this not too well. I don't know. Maybe it was a long time ago, but I've clicked on this before. Yeah. But okay, let's see. I gotta try and finish this. Pretty sure being a subgroup of Sn gives an upper bound on the degree of the irreducible representations. That is, well, yes. Yeah, but I don't know how useful that was. Your old street name was Young Diagrams. Wow, I'm definitely gonna steal that when I start my math rap career. Well, that's kind of cheating if you use the classification of groups of order divisor 24. 24 doesn't have that many divisors, all things considered. What? Isn't it technically a highly composite number? Doesn't it satisfy the definition of a highly composite number? Whatever that is. I mean, some approximate definition or something, right? But nice exercise to show that the automorphic factor is a cocycle. So it defines descent data from the trivial bundle on the upper half plane to some line bundle on the modular curve. Interesting. Let me make a sub note there. Yeah, somehow, side note, my master's thesis, which I still don't understand what I did, but I looked at a group mod this thing, and I was studying super vector bundles over this. And the point was, we did everything on this level where actually the vector bundle was just trivial. So technically very easy to work with. Wait, was it trivial? It's tautological. No, maybe it was trivial. Maybe it was trivial anyways. But the point was there's some discrete group that action you're supposed to take in this, and this vector bundle then descends to the quotient, and all the operations we were doing descends that quotient. I didn't understand what we were actually doing though. But Oedipus would have blinded himself by now. Modular forms are sections. Can anyone give a reference? Yeah, I think if you look at any book on modular forms, like if you look at Diamond and Sherman is a classic reference, so probably go look there, or Milne. Tomorrow's live stream, 8 hours of doing homology of torus. Maybe I still haven't made up my mind. but I'm thinking I might do it tomorrow. Well, no, I've got a lot of other stuff I need to do. Well, maybe I'll do it tomorrow. But you will understand, or at least try to soon. 24 is highly composite, but it's also small. Yeah. You forgot 8. Classifying all the groups of these orders on their own is also rather easy. Is it? Of order 8, yes. Of order 8, yes, but I don't know. Okay. Here's the thing. To try and finish this complex thing, we need to choose where we're going to send the faces to. And I guess... Wait a second. We actually have 3 edges. And so it's not so clear to me, because if we went D02, went to like, well, if we had both of these, if we had, say, both of these go to E12, then that makes sense, because then we glue them along here. But then what room do we have to glue these things, to glue the other edges together? How do we glue the other edges together? Yeah, Alufi does have an exercise classifying finite simple groups of up to order 60. I believe so, yeah. One must figure out where the faces get sent to. You can't just choose. What do you mean? No, we're choosing. We're choosing the sets, right? We're trying to set this up. We're trying to set this up to choose the sets to make this, to get something out that it's equivalent to the torus, homeomorphic to the torus, right? Like, we're still in the choosing part, and then we do the computing of the homology afterwards. Yeah, once we have the complex, but we don't have the complex yet. We don't even have the complex yet. Right? Here's the picture of T2, but what are the maps? And two simplices, yeah. We don't know what are the maps between the sets. You are choosing, but you have to make choices that's given by a torus, right? But that's what I'm saying. How is it? So I need to make a choice about where to send E20 and where to send E21. The maps are just usual alternating. Wait, no, these are, but no. I'm talking about the big deeds. So there's no alternating. These aren't maps of groups. These are just maps of sets, right? Oh, wait a second. These are going from the this is going from the set. Oh, I haven't been plugged in this whole time. Yeah, no, the maps DN, here are just set maps, right? The maps DN are just the set maps, right? It's just a sequence of sets together with maps. So I need to figure out what those are. The gluing data determines it. Yes, I completely agree with you, Leo. But what's the gluing data? Alternating in the sense of orientation. I don't get. So where do I send E20 to? D2 E2 sends E20 to. Have I taken graph theory? Yes. Graph theory. I also took a course on graphs and algorithms, and also did a reading course on spectral graph theory. Okay, so where do I send E20 and E21? Let's say we fix the orientation of both triangles to be clockwise. Well, can we say that we fix the orientation to be the one that I put here, the one that's on Wikipedia? E10 is on top. E10 is on top. This is E11. E11. E10. But where do I send E20? Like, it has to be a single element. It has to be a single element of S1. It has to be a single element of S1, right? Oh no, we're going to get stuck in the orientation indexing convention dimension? Well, gang, just tell me where to send this. Just tell me where to send this. I would switch to cell complexes and hand wave everything away, but no, that's cheating. D0 of E20 can be. Wait, you mean D1? You mean. Wait. DI goes from where to where? Oh, DNI. DNI. Oh, we have multiple maps. Right. I see. Hang on. We have multiple maps. So we have DNI. Right. DNI goes from here to here. I see. Okay. I see. So we have D. I see. Okay. So we have something like D20. We could have something like D20, E20 is E11, D12 of E0 is E10. Well, I guess we could just match indices, right? Maybe that's the more, but that seems weird for orientation purposes, but I'm definitely two-faced. Why are we doing this? No one uses singular homology to actually compute anything. Oh, I do, and I'm doing it now. I'm doing it now. And then D2 to E20 will be this, right? Yeah, I mean, I'm confused by the whole ordeal. But okay, now I understand. Now I understand. Now I understand. But we also need to make sure we have right, and we need some compatibility of maps, right? Now the other maps are all forced on us, right? Or by which I mean, since there's only one vertex, so D1I is E of E1J has to be E00. There's no other choice. Yeah. And then let's see, there's like one more compatibility condition that we need to check. What you would do by default, labels of n faces by n vertices. Yeah, that's probably a better way to do it, but right. And we need this composition law. We need this composition law. So we need that D. I don't have enough short-term memory to do that. So what do we need? We need D n I composed with D j n plus 1 is equal to D n j minus 1 composed with D n plus 1 I. And then you can define differentials in the alternating sum way. We do that anyways, right? I don't think that matters. Like the definition of the differential is the definition of the different. You take like an alternating sum of these maps or something, right? Okay, so then what are we doing? I guess I just want to make sure these maps that all of this is consistent. So let's check this for my, if I check this, so let's see, if we go D1I composed with D2J, and I test it on E2 0, for example, then it had better be D1 J minus 1 composed with, okay, so it doesn't matter because the D1s are going to be equal on all elements. So, great. Does it depend on how you label things? Because, like, if we go down here, you just take the free set. Yeah, it doesn't depend. It doesn't depend. Doesn't depend at all. Oh, maybe it depends on how you orient. Yeah, there's going to be some orientation thing maybe, but like this definition doesn't seem to matter so much. Yeah, but maybe you're right that there's you can get the signs right by just looking at it. Right. Can I just willy-nilly associate my other maps though? I need to choose the rest of my differentials. I need to make sure I choose the rest of my differentials to get this gluing. I guess I want to choose it to be the same, right? Because I want the equivalence between sigma and IT and d sigma I. And so, right. Sorry, I want equivalence here. And so, for example, if I have E20 inclusion of T being equivalent to E, have a good day to tenacity. Good luck classifying subgroups of S4. How are my croissants coming along? My croissant. Well, it's been a while. This definition doesn't seem to matter so much. Marks exactly the one definition where orientation matters. Oh, okay. Whatever. And then let's say I apply the map D20. So this should be equivalent to D20 of T. But that is going to be E10T. And I want to make sure that I'm gluing right along the inclusion of this boundary. So right, I want to make sure that this I want to make sure that I'm gluing these along the boundary. But yeah. And so D20 E20, right? Is that right? But actually, why couldn't this be literally any of the other differentials, as long as that differential sends it? So yeah, it seems like the order doesn't matter. The order doesn't matter either way. But maybe I'm crazy. But I think I can just make this definition. I think I can just define this in both cases to send this. No? Is that crazy? That seems right based off of this calculation. Yeah. But I guess I think that I think this is the way that I want to define it. Right? Because in that quotient now, like this is the thing that's gonna glue this E10 together with this E10, right? You can start at any face you want. Orientation only controls clockwise versus counterclockwise. I'm not sure I understand the comment. Like, I just want to make sure that this is the point T, right, included appropriately. Yeah, I'm pretty sure this is right. In order to get the gluing correct. So my maps are D2I of E2J is E1I. Just thank the Lord we aren't working with 3 manifolds, yeah. And then what am I gonna do? Then we know our other maps. Then we have that D1I of E1J is just E00. And then that's basically it, right? We're done. There's nothing else to say. If you imagine rotating the triangle before gluing it, you'll get the same torus. Well, as long as we're in agreement, these maps will give us the torus, because I've convinced myself that it's true. So now, what does the map D0 do though? Oh, dn goes from n+1. Oh, so sorry, I made this notation slightly incorrect then. I should be writing this as D1. And I should be writing this as D0. So there we go. And now our map is now our differential is wait, what's D sub 0? What's the definition of D sub 0? If S is a delta set, then the free abelian chain complex, the nth group is a free abelian group generated on this whose nth differential is this. But what is D sub 0? We've got like, what have I done? What did I just do to Wikipedia? No, what have I done? Control Z. No. How did I get here? Oh Lord. Okay, there we go. Mad boomer energy right now. Is that what we just want the orientation to be consistent? Now I'm really confused because we have D. What are these lower sums here? Well, it's like if you orient some edge opposite to before in any differential involving that edge. Okay. The superscript is omitted for brevity. Okay. Sure. Okay, so which... Oh, I see. Right, we're just omitting the superscript. Okay, right. So, right, we're omitting the superscript. So, die1 is going to be D1, 0 minus D1, 1. And die 0 will be D0, 0. Wait, I have 3 maps. Right. There's 3 maps and then 2 maps, so it's this. Wait. Oh God. Bro. I am cooked. No, yeah, there should be 3 maps. There should be 3 maps. It still makes sense. And then die 0, D1, D0, 0 minus D0, 1. Okay. Amazing. Del 2 for 2-dimensional triangles. Oh, del 2. I see. I should call this del 2 and I should call this del 1. Sure. Okay. So at long last, I think we're ready to compute, right? So we have this down to here, down to here, right? So now I just need to compute the kernel of del 2, and that should give me H2. Bogamath is a second-year undergraduate in mathematics, started doing research towards mathematical approach of neural networks, especially ReLU-NN. I have no idea what that is. And have found solution to the conjecture of Debauches? I don't know of this conjecture. Yes, express the torus in terms of a Leo complex, please. So let's see. 0 of del 2 on the span of E2 0 plus E2 1. How can you know if your work is valid or sound? Well, I mean, if you're an undergrad, then that means you're at a university. So if there's a professor in your department who works on the area, in that area, you know, you could ask them, you know, make a very carefully detailed write-up, and yeah, I don't know. Send them an email, ask if you can stop by their office, and present an idea that you know, say you've been thinking about that conjecture and you want to check your understanding, or something. Yeah. And ask them. That'd be one place to start. Sounds like a bit of a troll. ReLU is just max between 0 and a number. Very simple activation function. NN is just a neural. Okay. I don't see how that's a troll, though. How is that a troll? Yeah. Okay, so right, and what is this gonna be? So this is gonna be the sum of E1 0 minus E1 E1 1 plus E1 2 plus B E1 0 minus E1 1 plus E1 2. ReLU is simple and it produces CPWLs. Yeah. I know nothing of this thing. So basically the takeaway is that A plus B is equal to 0. And so, yeah, we can see that the kernel is going to be a rank 1 thing. So, nice. We did it, gang. We did it. Except, actually, the thing that we actually wanted to compute was the 3-hold torus. And, yeah, okay. This has thoroughly convinced me that this is not the method we want to use to compute the 3-hold torus. Okay. I'm satisfied. After all of this work, I'm satisfied that there's... Yeah, this is not the way to go. Okay, well, we finished this task. 3-hole way easier trust? Yes, I'm sure. I'm sure. So, but let me make a note here because I'm gonna end stream. But tomorrow, uh, tomorrow maybe we'll look at this. If you recall any, yeah, I have no idea what you guys are talking about with your machine learning stuff. Yeah. So great. A lot of blood, sweat, and tears for this, like, upper level undergrad problem. Oh, good lord. Good lord. Okay. See y'all later. And